We are all concerned about the breathability of living in this house, so let's measure the fugacity of all the pollutants in here. Fugacity. F-U-G-A-C-I-T-Y. Fugacity. My chemical engineering friend introduced me to the term fugacity by saying that she studied it along with a whole bunch of other fellow chemical engineers back in college, and even after studying it and taking tests on it and doing a lot of math on it, she still didn't really know what it was. So I went around doing a little bit of research, not just on Wikipedia, but also in some journal articles, and let me take a stab at summarizing fugacity. Fugacity is a lot like pressure. It's a property of gases, and actually a property of all sorts of states of matter and substances, but people tend to talk about it in terms of gases. And gases have a pressure, right? The higher the pressure of a gas, the more energy is stored inside that gas, and the higher likelihood that molecules of that higher pressured gas are going to escape if the gas was contained in some kind of container. So imagine you've got a soda can, for example, full of air, and it's sealed. Well, if you say that the gas has a higher fugacity, it means that that gas inside has a higher chance of escaping that can, maybe through some little crevice or something. Engineers or scientists will talk about fugacity when they're interested in whether or not a gas will escape from a compartment or not, like, for example, in pollution studies. So that's what fugacity is generally, but it's certainly related to pressure, right? The higher the pressure is, the more likely the gas will escape. So why do we even talk about fugacity at all? Why don't we just say pressure? Why don't we just say, hey, the higher the pressure of the gas, the higher the likelihood of escaping from this compartment? Well, the truth is that fugacity, or the tendency to escape a compartment, is not due to the pressure alone. It's very, very closely related to pressure, and for ideal gases, it is pressure. For ideal gases that are simple and that obey the simple mathematical chemical laws that we've learned in high school, yeah, fugacity is pressure. But in real life, not all gases are ideal. And the fugacity that you see in reality might be a little off from what you might predict based on the pressure alone. Just be aware that fugacity is kind of you could call it a fudge factor, or a way of correcting the reality that we see with what we might predict with equations. I think that one analogy might be with my car. My car has a theoretical mileage value. It has a theoretical efficiency where I can get a certain number of miles per gallon of gas. Maybe it's 30 miles per gallon. I drive it around, and I expect, if I have 10 gallons of gas, that I can go 300 miles. But in reality, of course, I don't get that. I get 250 miles, let's say, on those 10 gallons of gas. My car is not ideal. And it behaved as if it only had like 8 or 9 gallons of gas in there. So I would need some kind of fudge factor to correct for that. Fugacity is like that situation. We can understand how gases might behave in an ideal scenario, and we might use pressure to predict that behavior, but fugacity helps us account for reality, and we aren't just looking at pressure alone. We got to look at the particular gas and what's happening with its molecules. Fugacity helps us go from the ideal predicted behavior to the real, a little bit more messy behavior of a gas. Fugacity is our engineering word of the day. Hi, this is Pius. I am host of the Engineering Word of the Day podcast and also host of the K-12 Engineering Education podcast, all about bringing engineering education to young people. If you'd like to listen to that longer podcast, go on over to k12engineering.net and let me know what you think. Thanks.